All right. One thing that I would like to say before I start, I said this last week. I like saying it every year. If you've had me in class before, you know I am slightly unhinged, and I use that word "slightly" very loosely. My goal here is not to be your friend. I try to be friendly with all of you. I try to be nice. I try to know all of your names except for mustaches over there. Which I could call you Man Bun now.
That works.
That's not an improvement. I try to know all of your names. I try to know where all of you want to go. I try to help you with where you're going in life. But I am not your friend. At the end of the day, I'm your teacher. And as your teacher, it is not my job to tell you jokes and when you make mistakes, pat you on the back, give you a good butt slap and say, hey, get up and do it again. You're doing great. Or, oh, you tried. Good job. It is my job to push you to succeed. This class, for most of you, is not within your emphasis area. Electrical engineering is not something, quite frankly, as a civil engineer, if you're going into to try to be a civil engineer, electrical engineering is not something you probably have any passion for whatsoever. And that's normal. I've had many students come and tell me in this class that electrical engineering is stupid. Well, it both is and isn't. I've had those same students later tell me they never wanted to take a class with me again, but that's different. This is not a class where I am trying to be your friend. This is a class where I'm trying to help you grow and understand this material. It is not uncommon in today's world for civil engineers and electrical engineers to work together. And in fact, I am a member of the American Society of Civil Engineers, and it's common for civil engineers to tell each other, you should get a degree in, you should go back to school and do some studying in computer science. You could learn some programming. I had just got off a phone call last week with a civil engineer who works for Valmont, and he told me point blank, I wish I would have taken electrical engineering courses because at this point he is designing power substation supports. And he is actually designing the supports for them, and the way that all the componentry mounts to the support structures, he says, I know there's inefficiencies there, but I can't point it out because we can't even talk to the electrical engineers. We speak a different language. This class is required by DONE, not because this is, we're just low on classes for you to take. This is deliberate. Electrical engineering and the foundations of electrical engineering in this course are good for every discipline to know. Understanding these principles will help you better understand instrumentation, which every engineer needs to know how to use an instrument. Every engineer needs to know how to take measurements, how to do basic signal processing, how to understand what is a circuit. Every engineer should know how to build little tiny electrical devices. It's one thing I wish I would have known when I was in school. So this class is not going to be fun for some of you. It's going to be a lot of fun for some of you. And for the rest of you, you're going to look back on this, waking up at 8 o'clock in the morning as, you might have nightmares about it afterwards. We are going to get into course material that has kept me up at night. So, yeah, good times. Just wait till we get to RLC circuits. If you have heard recommendations from anybody who has taken this class before, I do teach this class hard. But again, my goal is not to be friends with you. It's to push you to grow. So, that's my spiel. Now, that said, in order to get to this point in your education, in order to sit in this class, you have to be smart. You have to be pretty dang smart, okay? We're not talking like, oh, I accidentally wandered in this class from the cornfields. I'm here because you guys have been through physics 1, physics 2, calculus, higher level calculus courses. Most of you have either taken or are currently in advanced calculus class, which involves differential equations. This is something where you're here not by accident, but because you've put in a lot of work, okay? I make this class challenging because it's my job not to hold your hand and tell you how great of a person you are, but to help you be an even better person. Now, I will sit down and tell you how great of a person you are because I like being encouraging. But at the end of the day, this should challenge you. If it doesn't challenge you, I'm not doing my job very well. And it's going to challenge you because nobody understands these things just naturally. If you come into this class and you know how to handle voltage in a capacitive circuit, get out of here. Because I already envy you. I'm turning on these lights too. Which nobody likes at 8 o'clock in the morning, but I don't care. All right. We are going to begin lecture today. And one of the reasons why I didn't want to do this on Tuesday, virtual learning just sucks. And this is hard material. Okay, it starts off not hard, but then it goes into mildly insane very quickly. So what we're studying here is resistance-only circuits. Now what does that mean? It means we are looking at circuits that only consist of resistance elements and power supplies. That's it. Okay? It also means in every single problem, you're going to need to know Ohm's law. I'm assuming all of you know Ohm's law. Joel does a really good job of teaching that in physics too. Please tell me all of you know Ohm's law. Please tell me any of you know Ohm's law.
We went over it.
Huh?
Yeah, we went over it.
What's the formula? I also gave it to you in class last week, so you really don't have an excuse. Yes. V equals IR. Voltage is equal to current times resistance. There are three relationships that we have between voltage and current. Three relationships. Okay. One of them is for a resistor. One of them is for a capacitor. One of them is for an inductor. We won't get to the relationship between voltage and current for the capacitor and the inductor until the next chapter. The reason why we hold off on that is because, quite frankly, there are integrals involved, and that's a nightmare. So our goal here is to really hone in on what is a resistance-only circuit and figure out what we can know. Now the first part of this class is going to be dedicated to understanding parallel and series components. Okay, this isn't going to involve new formulas, asterisk. we're going to derive some new formulas and some new relationships. Okay, so first of all, let's start off by discussing what is series. Okay, in order for components to be in series, this is two or more components, what it means is that current flowing through one component will flow through the next component sequentially. If you think about like a water pipe, that's not a noodle, that's a pipe. If water was flowing through this pipe, and then you have another pipe, preferably connected, but I disconnected them for the sake of argument, and you have water then flow from this pipe into this pipe, they're connected in series. Pretty simple. Two pipes connected to each other, current flows through both of them. Same direction, current doesn't stop and flow backwards in one pipe. It just flows through both. Similarly, if you have this is a resistor, this is a resistor, you have electrons flowing through this resistor, and this connected to this one, they're going to flow from this one to this one, it's just going to pass on through. Okay? So that's series. Parallel is a little different, okay? In parallel, voltage applied to one end, applied to both ends of a component, or applied to both ends of both components, if that makes any sense. So voltage is applied across both components. If you think about it like that, it's if you have a bend in a pipe where the water splits into two directions, okay? You have water coming in, you have some water going this way, some water going this way. We don't know how much water is going through which branch. It's usually a property of the resistance to flow in those branches. And then we have two components here. The idea is they're going to be at the same pressure, which is similar to the energy level that an electronic component has. The pressure drop across these pipes will have to be the same because they start at this pressure, P1, and they end at this pressure, P2. Okay, here in these components, you can have a pressure drop across the length here, such that this starts at P1 and ends at P2. This component itself does not have to end at P2. It can end at P1.5. Or it doesn't have to have the same pressure throughout the system. Here, these two components do have to have the same pressure. Otherwise, you're going to have water flowing through this pipe, and then because this one's at a lower pressure, shooting back through this pipe, which doesn't make any sense because where's it going? The only way that's possible is if there's a leak in this one and you have water flowing out of it. These components, yeah, that was just a hard table to see this side of the board. These components have to be at the same pressure level, okay? And that's what voltage is. Here, current is constant between these two. Here, voltage is constant across these two. Now, I'm going to go ahead and derive this relationship using Kvl and Kcl. As I told you, those are some of the, I gave you like 6, 7 equations, and said those are all the equations we need for this semester, I'm going to go ahead and derive this relationship using Kvl Kcl. Probably shouldn't go any further on this board. All right, so what I'm going to go ahead and do is I'm going to say here is it's a DC voltage source. We'll say that this is plus 10 volts. We're going to go ahead, put a resistor here. We'll put a resistor here. And then we will branch off and have two resistors coming out over here. Okay? I will call this one R1. This is R2, R3, and R4. Okay, now, because we're good, am I drawing on the camera? Yeah, I am, okay. Because we're good at creating these diagrams, we're also going to go ahead and label nodes. This is node 1, 2, we'll make this node 3, and this node 4. Now remember, nodes are anything that you could, that doesn't have a component is part of a node. So everything from here to here, those two branches are all the same node. This branch, this branch, this branch, there's no components inside of that region. So it's all part of the same node. Okay, similarly here, that's all part of the same node. This is all part of the same node. If we were to try to draw another node right there, it could be merged with two very easily. Okay, so we have 4 nodes on this system, and we have 2 loops. We have loop 1, which goes inside the system, and then we have loop 2, which goes outside the system. So you have one that goes through this inner resistor, one that goes through the outer resistor. You could draw a third loop here, but as I pointed out in lecture last week, that means one of the resistors has to be considered negative because you're going against the flow of the current. Okay? So, here is the circuit that we have. Now, we have a 10 volt power supply. I'm not going to give you the resistances because we will talk about that very shortly. But let's go ahead and say that this has 1 amp of current coming out of it. Now, because this is a DC voltage supply, the current coming out of the battery depends on the circuit. That's kind of a foreign concept. This does not always generate 1 amp. If I were to put another resistor in here, it would change the current coming out of the battery. Battery current is driven by the system. Voltage is driven by the component. If you had a current generating element, the current is generated by the system, and then that means the voltage is driven, no, the current is generated by the component, the actual battery, and then the voltage would be determined by the system. So, yeah, we're already getting into confusion, and this is day 1 in class. Huzzah! We have 2 loops, which means we have 1, 2, 3, 4, 5, 6 equations. Okay, we'll start with KVL. KVL focuses on the loops. So for loop 1, you have VR1 plus VR2 plus VR3 equals VS. What's the equation for loop 2?
R3 by R4.
What was that? What do I write?
I said it just squeezed the R3 by the R4.
Yes, actually, it's the same equation because VR1 shows up in VR2, but then you switch VR3 for VR4. Okay? Good call. And do you pronounce it Henrique?
Whatever you want.
Henrique?
That works too.
Just give me one, man.
Henrique?
I will call you Mustache too. I can't call you Man Bun if you take it out.
So do you want that? Man bun or not that?
I don't even know, okay? I'm gonna have to start calling you Sal from now on. You have to make this so hard. I'm really glad you're good-natured because I give you a hard time. Okay, so these are the two equations. From here, what we can figure out is, I'm going to call you Henrique until you tell me otherwise.
Henrique?
Henrique?
Whatever you want.
Is it Henrique? Can somebody else help me? What is it? What?
It is.
It's okay. We're going with that. Okay. So I'm bad with names. You got to pick one and give it to me. Like, I think when I first met you, I called you Salvador, and then you were like, "No, call me Sal," and I'm like, "Okay, I'll stick with Sal." And then I stopped calling you Sal. That was a really bad example. Okay, so for these two equations, as Henrique pointed out, the only difference is these two. If you combine these two by bringing VR1 plus VR2 over to this side, what you end up with is VR3 is equal to VS minus VR1 minus VR2. You also find out that VR4 is equal to VS minus VR1 minus VR2. Okay? With these two equations, they're both equal to the same thing, which means they're equal to each other. VR3 is equal to VR4. We already said that. Because these components are in parallel, they have the same input and the same output, meaning they're in parallel. If this was a pipe, water flows in here, branches into two directions, travels parallel to each other, converges, goes back together. These components are in parallel. Now, are VR3 and VR4 in parallel with VR2? No. VR2 has an input at node 2 and an output at node 3. VR3 and VR4 have an input both at node 3 and an output at node 4. Okay, so if we draw a little bit of a chart where the components go, and here's input and output, R1 has an input at node 1 and an output at node 2. Okay, R2 has an input at node 2 and an output at node 3. R3 has an input at node 3 and an output at node 4. Similarly, R4 has an input at node 3 and an output at node 4, meaning they're in parallel. Okay, it's a little table that kind of organizes where everything flows. R1 flows from node 1 to node 2. R2 from node 2 to node 3. Okay? So, using our Kvl equations, we proved that these two are parallel. All right, if we go ahead and use Kcl, we have 4 equations we can use. Okay, we'll start at node 1. What is Kcl equation for node 1? Well, first of all, what is Kcl? What's that? Yeah.
It's like the current is equal from whatever goes in to what goes out.
Right. All the current going into a node is equal to all the current going out of that node. You don't have a current that just suddenly stops, hangs out, and wants to, just want to be with my bros. It doesn't do that. It moves. Okay, current electrons don't suddenly stop for no reason unless it's a capacitor. But wires are not capacitors. So, current going in equals current going out. Kcl equation, in equals out. What is the Kcl equation at node 1? What current goes into node 1? If we're following our loop, current is going this direction. So what is this component right there? It's our source. So the input is equal to IS. What is the output equal to? Where does the output current from node 1 go? Well, what node does it go to? It goes to node 2. So I can go ahead and rewrite this as I4 to 1 is equal to I1 to 2. Because the current going from node 4 to node 1, which that's that line, is equal to the current going from 1 to 2. We know that the current going from 4 to 1 is equal to the current that goes through this component. It's because that is what the current is, which makes it I source. And the current going from 1 to 2 is equal to the current going through R1, which makes this IR1. I can't simplify that equation anymore. It doesn't get any simpler than 1 equals another. I mean, the only way it could be equal, it could be easier is if both of them are 0. Or infinity. So we'll go on to the next equation. What is the Kcl equation for node 2? What is the input to node 2? What's that?
I1 to 2.
I1 to 2, yes. Because the input to node 2, the current flows from node 2. The current flows from node 1 to node 2. Okay? What's the output from node 2? It flows from 2 to where? I2 to 3. Okay? So I1 to 2 equals I2 to 3. What is I1 to 2? What component defines what that current is? It's R1. So this is IR1, current flowing through, component R1. Well, what defines current flowing from 2 to 3? It's R2. So IR1 equals IR2. Well, that's kind of a dumb equation again. This can't get any simpler than that. The current that flows from the source is equal to the current that flows through R1. Why? Because they're in series. Because they are in series. And because there's only one input, one output. That's what Kcl says. Okay? Current flowing from 1 to 2 is equal to the current flowing from 2 to 3. So the current flowing through this component is equal to the current flowing through this component. Why? Because they're in series. Now things get a little funky at node 3. What's the input to node 3? Where does current come from? So it's I2 to 3 is equal to, okay, where is the output from the current coming into node 3? Where does that go? It goes to 4. I3 to 4. There we go. Go ahead and draw my arrow points too. Okay, so what is the current flowing from 2 to 3? It's the same as IR2. So we can go ahead and write IR2 there. Okay, what is the current flowing from 3 to 4? Yes. We have two components here that define the branch out. It branches out at node 3. So we have two outputs. Those two outputs between 3 and 4 are both IR3 and IR4. So this is equal to IR3 plus IR4. Okay? Now, when we're looking at this, is IR3 equal to IR2? No, why not? Yeah, because there is an IR4. Assuming that IR4 is not 0, this is not going to be equal to this. But they're in series. I'm off camera so I can do this. I try not to sing on camera too, but every once in a while that doesn't happen. Particularly in this class. I don't know what it is about 8 o'clock in the morning. I am not that cheery of a person in the morning, but I tend to sing in this class. I think I just love this class a lot. So the rules are a little weird here. If you have one input, one output, the components are in series, then you know that the current is equal between them. These two components are in series, which means that their currents are equal to each other. Okay? These two components are in parallel, which means their voltages are equal to each other. These components here, between 2 and 3 and 4, are in series, but they do not have the same current. Because there's two of them and it branches. Okay? But we still know that the sum of those two currents is going to be equal to the current that flows through IR2. So take that as your series equation there. Okay? All right. Have I thoroughly confused you now about series and parallel? Yeah.
So if you did node 4, you would have IR3 plus IR4 equals IS.
Very astute. Very. Because yes, that's true. I3 to 4 is equal to I4 to 1, which is equal to IR3 plus IR4 equals IS. That's what Gabby just said. And yes, that equation is true. We could have also gotten that equation from combining these three, which is part of the reason why I got lazy and didn't want to write that fourth one. You always got to call me out, so good job. The thing about this is this equation can be derived. All of your Kcl equations, turns out you have the number of nodes minus 1 unique equations. You can derive the last equation using the rest of the equations. That's just fun math. It's the way it works out. But you can write out all equations, that doesn't hurt. These are all the equations that are possible, et cetera, et cetera. So it's the same way with the KVL. Technically, we could have had a loop here, but we didn't, so I didn't write that down there. I don't like any loop that doesn't include the source voltage. All right, any other questions on series and parallel? Does it kind of make sense? Kind of making sense is good. Dylan, you're giving me a look. Okay. All right, as long as it kind of makes sense, we're in a good place. All right, let's do an example. No, let's not do an example. Let's jump into the early ideas of, okay, now how do we use all of those fun equations that we just wrote? Because you don't know how to solve any problems yet. We've been setting up problems, and what we just did right there, I mean, we set up a problem, that was perfect. But now what? And now we're getting into the now what. Okay, so now you have a system. that has a number of resistors in it and some power supply. Okay, I am going to focus mostly on DC voltage because those are the more common circuits. A DC current generator is very rare and incredibly difficult, and the reason for that is in a DC voltage, your power consumption decreases when you increase the resistance. In DC current, the power consumption increases when you increase the resistance. It's a weird phenomenon, but we'll talk about why in a little bit later when we actually get into the first time I draw a DC current source. So I'm just going to give you a very, very simple circuit. You have a power supply. You plug in a single resistor. This power supply, Vs, is equal to 5 volts. This resistor, R1, is equal to 120 ohms. What is the current? Question here is, what is the power output from the battery? How much power is being consumed? Okay, can anybody answer this one without me having to walk through this? Yes. Wait, are you going to answer this one? Just say no and let's keep going. Yes. Okay. How do you do this? Well, first we need to know, let's look at the overall equation. Power coming from the battery. What is the equation for power? I gave that to you last week. P equals VI. Okay? So power coming from the battery means we're looking at P source is equal to V source times I source. V source times I source. That's what we're looking for. Okay? Now, do we know either V source or I source? We know V source. What is it? It's 5 volts. So we know this one. Do we know I source? No. How do we figure that out? In a battery, if this is a voltage supplying power source, what that means is that this will generate 5 volts and it will do whatever it takes to make 5 volts happen. Okay? And in AA, they put out 1.5 volts. And if you increase the current traveling from one end to the other, it will do everything it can to produce 1.5 volts until it reaches its current limit. There's only so much current you can draw out of a AA battery. Once it reaches that limit, then the voltage will drop. But assuming that it is able to output the amount of current that the circuit wants, it will put out exactly that much current. It's almost like the two ends of the battery can read what the rest of the system is doing. That's going to come into play later in this class. Later today in this class. Okay? So, we need to figure out this value in order to solve the problem. In order to figure out this value, what I just told you was that this value depends on what the rest of the circuit looks like. Okay? Which means we need to find out what the rest of the circuit looks like. And then we'll get back and figure out what IS is. All right? So, we'll go ahead and establish our nodes. 1, 2, and we'll go ahead and establish a loop. We have one loop, L1. Should make things easy when we do KVL. What is our KVL equation for loop 1? First of all, what is KVL? And we only have one VR1, so it's going to be just VR1 equals VS. So VR1 equals VS. The power that's consumed in a loop is equal to the power that's generated for that loop. Or the way that I presented it last week was you just make VS negative, but that's really what it comes into. Voltage out equals voltage in. Output voltage is VR1. It's where the power is being put out of the system. Power is being put into the system through VS. So power in, power out equals power in. All right? We don't have any other equations for KVL because we only have one loop. We only have one component, so that was easy. Okay, KCl, we have two different nodes. At node 1, what is the Kcl equation? KVL focuses on voltages. KCl focuses on currents. KVL is about loops. KCl is about nodes. What is the equation for KCl at node 1? What is the current coming into node 1? It's coming from 2 to 1. It goes to the source. So I'm just going to go ahead and write I source. Okay? What is the current going out of node 1? It's going from 1 to 2, and it's going through R1. So I'm going to go ahead and write that as IR1. Okay? At 2, your equation is the same. The current coming from 1 to 2 goes through R1. So it's IR1 is equal to the current going from 2 back to 1 is equal to IS. It's the same equation, just flipped. Which means we only have 2 really other equations that we can use. We got this one, we got these 2, and we have one last one that we haven't written down yet. Ohm's law, yes! Nice work, following. So the thing that I haven't written down yet is this is a resistor. This is not a resistor, which means Ohm's law doesn't apply. This is a resistor, which means Ohm's law does apply. Because Ohm's law applies, we know. So at R1, we know Ohm's law is true, which means that VR1 is equal to IR1, let me go ahead and make that a lowercase, times R1. Do we know VR1? Huh? It's 5. And we know that because in this equation, VR1 equals VS, and we know what VS is. So, yes, we're good here. Do we know IR1? No. Do we know R1? Yes. If you have 2 out of 3, you can figure out the third. Okay? So here, IR1 is equal to VR1 divided by R1, which is equal to, what is VR1? It's 5 because it's equal to VS. 5 volts divided by what is R1? Oh, dang. Should have made that a nice number. Let's just make this 20. The unit of resistance is ohms. So 5 volts divided by 20 ohms. Because you didn't see me write a 1 there. I was a scratch on the board that I erased with my thumb. Is equal to what? What is IR1? What is IR1? 4, what's the units on it? 4 amps. Okay, which 4 amps going through a component is redonkulous. Okay, 120 ohms was a lot more realistic. But whatever, it's what the math says. We blindly agree with math. Okay, so we know that IR1 is equal to 4 amps. Does that help us at all? Henrique says yes. Why does that help us? We're looking for IS, not IR1. Because of this. Yeah. So we know now what IS is. What is IS? It's 4 amps. Okay? So now we know this one. We know this one. We can calculate for what the last one is. All right. So power coming out of the source is equal to the voltage coming out of the source times the current coming out of the source. What is the voltage coming out of the source? It's 5 volts. What is the current coming out of the source? It's 4 amps. Which means, what is the power coming out of the source? It's 20. What is the unit? No, that was a statement. Watt is the unit. This is probably one of the reasons why this is my favorite class. The joke is terrible. I tell it every year. Watt is the unit? What? What? I do have problems. Okay. We're going to go ahead and take a 10-minute break. Try to break up this monotony. I will see you back here at 9:05. Okay? I'll start a brand new video at 9:05.